Today, I will walk you through one of the most impactful technologies in modern software development, containerization, and the tool that popularized it, Docker. Containerization means packaging an application with all its dependencies, like libraries, configurations, into a single isolated unit called a container. The main goal is consistency. Whether you run it on your laptop, a test server, or production, it behaves the same way. So, why is containerization so popular? There are three main reasons. Portability. Containers run the same anywhere. No dependency issues. Speed. They're lightweight, so deployment and scaling are extremely fast. Efficiency. Unlike virtual machines, containers share the host OS kernel, using far fewer resources and starting almost instantly. Here's a brief story. Containerization isn't entirely new. In 1979, Unix introduced crude for process isolations. In 2000, FreeBSD jails provided early container-like environments. Then in 2013, Docker made this concept simple and developer-friendly, marking the real revolution. And by 2015, Kubernetes emerged as the go-to tool for managing and scaling containers. Now, what is Docker? Docker is a platform that automates application deployment using containers. It consists of three main parts. Docker Engine, which runs and manages containers, Docker CLI, which lets you interact with Docker through commands, Docker Hub, which is the central registry for storing and sharing images. Together, they make containerization accessible to everyone. Now, let's see the Docker architecture. Docker follows a client-server model. Client runs command and Docker host runs the Docker daemon, which manages images and containers, and the registry stores images. When you run Docker pull, the Docker fetches an image from the registry. Here are the three key terms you will often hear are image. The blueprint, it contains everything your app needs to run. Container, the live running instance of that image. Docker file, a simple text file with instruction on how to build an image. Here's an example of Docker file. A Docker file might start with a base image from then copy your code, run installation commands, and end with cmd, defining how the container starts. It's simple, repeatable, and ensures every developer builds the same environment. Here are a few commands every Docker user knows. Docker run to build Docker image, Docker ps to list running containers, Docker images to display all Docker images available locally, Docker pull to download the Docker image from a registry to your local machine, Docker exec to execute command inside a running containers, Docker stop to stop container, Docker rm to remove containers, Docker build to build a Docker image from a Docker file, Docker logs to fetches log of a container, Docker inspect to shows detailed information about a containers. Here is the Docker Hub and registries. Images are stored in registries. Docker Hub is the main public registry full of reusable images. For private projects, companies use secure internal registries like AWS ECR or GitHub Container Registry to manage their image safely. Now, here's the key difference between containers and virtual machines. Virtual machines each run their own full operating system on top of a hypervisor's heavy and slow to start. Containers, on the other hand, share the host OS kernel. They are lightweight, faster, and most efficient, perfect for modern app development. In a typical DevOps setup, code is built and tested using tools like Jenkins. A Docker image is created using a Docker file. Kubernetes then deploys that image to production. This ensures every release is fast, reliable, and identical across environment. A few best practices to keep in mind. Use lightweight base images like Alpine to reduce size. Never include secrets inside Docker files. Regularly scan images for vulnerabilities. Use multi-stage builds to separate build tools from runtime code. Always set CPU and memory limits for containers in production. Here is the Docker volumes. By default, containers are temporary, their data disappears when stopped. Docker volumes solve this by storing data on the host system, allowing persistence, easy backups, and sharing data between containers. The Docker ecosystem. Finally, Docker sits at the center of a vast ecosystem. Docker Compose for multi-container setups, Docker Swarm or Kubernetes for orchestration, registries for image management, and security and monitoring tools to keep everything reliable. This ecosystem is what makes containerization powerful and scalable. Now, let's start our next part. I started by opening Ubuntu 25.04 in my virtual machine. Then I logged in with my password and username. Then I verified my internet connection by pinging google.com. Next, I removed any existing Docker GPG key and repository list to avoid conflicts from older installation. Here I got some error. Let's fix this. Now I ran sudo apt update. Then I installed the required dependencies. It shows that I have already downloaded this. Next, I created a directory for Docker skidding. Then I downloaded Docker's official GPG key using this command. Then I checked the ISP release and I got its plug key. After that, I tried to add the Docker's repository with an echo command. Okay, this shows an error. Let's see by which sudo. There wasn't a mistake by sudo because sudo was actually installed. Let's see without backlash. I removed the backlashes. These also, and run. Let's try updating by sudo apt update. Okay, this shows an error. Uh, let's try again. Okay, this is here I mistakenly written signed by is equal it's etc/etc. So that was the actual error, and I fixed it and updating again and installing Docker engine using this command. Now checking the Docker version. Before connecting to Docker Hub, I set up Docker's configuration directory. I created the folder. Then I opened the configuration file with this command. Inside this file, I wrote a simple authentication structure. This ensured Docker could store my credential properly. Then I logged out and then Docker login, giving the proper information. Okay. This shows that I need to verify my email and I did it. Then it shows that my login was successful. After that, I started step 3. I pulled all the required images from Docker Hub using sudo docker like this. Next for MySQL. This also done. Next is Redis. After that, Mongo. And next we have HTTPD. After all downloads completed, I verified them with Docker images, and all 5 images appeared in the list. In the next step is container creation. I created containers for the web server using this command. Checking for all the containers. Then I ran docker ps to confirm both containers were running in detached mode. In the next step is docker volumes. I created a volume named my data using this command. Then I attached it to a MySQL container. By running this command. To confirm, I inspected the volume with this command. In the next step, I listed existing network using docker network ls. And then I created a custom network is mynet. Next, I ran 2 containers inside that network. Next, to test connectivity, I used docker exec. Initially, there was a name resolution error, but after checking with docker network inspect mynet, I confirmed both containers were connected successfully to mynet. And finally, I viewed image history and container logs. As you can see, both commands work as expected.